Hello, this is Xavier Jacques, Deputy Lead of Team C.R.A.T.E.R from Lone Star College Sci-Fair. We're so excited about returning to TSGC this semester since we put so much work into it since the last time we were here. I just want to thank you all for watching our presentation, and take care.
This is the second semester of our MicroG challenge. Well, what is MicroG? MicroG gives undergrad students an opportunity to design, build, and test a tool or device that addresses current space exploration. Team C.R.A.T.E.R has accepted the challenge to create a dust-tolerant pivoting mechanism for the lunar surface. Through NASA's 2024 Artemis program, we'll use innovative new technology, tools, and systems to explore more of the moon. From NASA's past moon exploration, it was discovered that lunar dust is problematic for the devices and tools the astronauts use during the Apollo mission. Lunar dust is likely to get into the mechanisms of the tool and limit its effectiveness. There is a need for lunar surface tools to be compatible with the harsh lunar environment to ensure that they can be used repeatedly in a mission without any issues like binding or jamming. Some tools require a pivot mechanism to change the angle of the tool head, like adjusting the angle for a shovel to allow it to collect samples or act as like a trenching tool. The kind of uses the mechanism will be under are extreme, such in use for geological work, mechanical work, and even machine work. Our team is tasked with overcoming these obstacles and more through the MicroG challenge. And with that, I'll pass it on to Robert for research.
Thank you, Daniel. To better understand the challenge that a lunar environment poses, we did research into the properties of the lunar dust. We discovered that it was a 45-meter layer of dust, and that the dust is magnetic, adhesive, and abrasive. That means that the lunar dust determinately affects all aspects of lunar exploration because it can damage mechanical equipment and even astronauts' health. Other research we did this semester was into different materials we could use to our device. The most promising material we found was polyether ether ketone, or PEEK. PEEK is a great material because it's not very heavy and it has excellent mechanical and thermal properties. These properties can be made even better if PEEK is filled with fiberglass or carbon fiber. We also found ways to combat the immense planetary delivery cost by looking to possible applications of 3D printing in space. Since PEEK can be 3D printed, that would allow for the astronauts to print tools and repairs on site, which would help lower the cost. But ultimately, we decided to forego the use of PEEK in our device due to the requirements laid out by the MicroG challenge. And I'll let Edgar explain what those are.
Thank you, Robert. The first thing I'm going to talk about is the design specifications laid out to us by MicroG, which played a big role when it came to our preliminary design and ultimately our final rendition. We set out to create a dust-tolerant, manual-powered pivot mechanism that has the ability to lock at the 0, the 45, and the 90-degree angles. It needs to have a minimum length of 30 inches and be operable with EVA-gloved hands. Also, the total weight of the entire tool needs to be less than 3 pounds. The device needs to be safe. It cannot have any sharp edges, and all the pinch points need to be minimized and or labeled. Finally, the tool should be made from aluminum, stainless steel, or Teflon. This requirement is specified because these are the only 3 materials currently approved to handle lunar samples for the Artemis mission. As far as our design process goes, this entire semester we were basically stuck in 2 stages, and those consisted of improve the design, test, improve, test. As aspiring engineers, we share the idea that the design process is never truly finished. There's always a way to make things better. In that effort, we made a lot of changes to the device that was presented last semester. Now, unfortunately, this semester our team faced unexpected and difficult challenges. Obviously, we all felt the blow of the COVID-19 pandemic and its impact on our ability to collaborate. And for our project specifically, we encountered numerous issues pertaining to elements of our design. The first of which being the use of magnets. We discovered that the magnetic flux could interfere with the EMU electronics on the EVA spacesuit, and as such, we had to completely rethink the retention handle. The second major design modification was a material change due to miscommunication with NASA. With only weeks before our deadline, we had to find a way to reduce the weight of our device due to that material change. We were afraid we wouldn't be able to meet the goal, but fortunately, with a strict diet and some rigorous exercise routines, we rose to the occasion and we were able to remain under the 3-pound limit. These are just some of the challenges that we faced in the last few months. But in light of all of that, we're actually really proud of what we've managed to accomplish, and we hope NASA will be as well. I will now pass it on to Carrie, who will get into a little more detail about the changes that were made to the ARMS design.
Thank you, Edgar. With the design of a device such as ARMS, functionality is the utmost concern. That being said, its interface with the astronaut, and particularly an astronaut with restrictive EVA gloves, is also just as vital as the functionality of the tool. As previously mentioned, we reassessed the device with intense scrutiny given the feedback of all of the professional reviews we received, and adhered to those and more. We began with a rethinking of the handle from a T-style to a hoop style. This reduced the chances of sliding off the side of the handle as well as reduced the fatigue on the hand. Attached to the new handle, we converted our previous handle extension into a larger OD perforated and rib style handle that allowed us to have more modularity as well as increase the strength by enlarging the outside diameter. Moving to the pivot mechanism, this was our primary functional component of the device. For dust mitigation, we converted our axle and lock pin shaft seals from a press fit to a threaded OD style. This allows for quick and easy changing of the seals as they wear over time. One of the most immense hurdles of the device was the weight requirement. Through lengthy design iteration and cross-examining different methods of weight savings, we believe we came up with the best strength-to-weight ratio possible. The unlocking and locking features of the device were improved by eliminating the magnetic retention feature and implementing 4 sealed spring-loaded detents within the housing. This is in a completely sealed environment, so this allowed us to eliminate any contamination issues with the lunar dust. These detents are robust enough to hold the locking handle retracted, but also easy enough to overpower with a small additional force to change positions. This also provides a nice feedback for the user to feel which position he's in before changing the angles of the tool. We wanted our device to be the most durable, high load capacity device possible. To increase the locking strength, we extended the housing body to allow for a more full penetration of the lock pins into the axle. This allowed us to also add 2 more fasteners to help hold the housing halves together more secure. Lastly, in the spirit of redundancy and safety, we converted our center arm to an interlocking configuration. This interlocking configuration prevents the center arm from being able to be removed while in the housing. So in the event that the retaining bolt would fall out of the center arm, the astronaut could rest assured that the attachments would never fall or slip and create an unsafe environment. Now, Xavier will be talking about the testing and what is to come next with ARMS device. Thank you.
Thank you, Carrie. For the testing of the ARMS device, our team put it through the same testing procedures that we're expecting at the Neutral Buoyancy Lab in September. Using a combination of both a wet and a dry environment, we wanted to see how our device would perform. And as you can see from the footage, we can confidently say that given a real lunar environment, our tool more than adequately performed to the task, demonstrating flawless actuation even in the testing environment. We're excited to see our device tested at the NBL and get feedback from NASA on all the hard work we've done over the last 2 semesters. But for now, I'll pass it off to Humberto, who'll talk about the outreach we did this semester. Thank you so much.
Last semester, Team C.R.A.T.E.R, alongside our sister team, Team Cosmos, were honored to have the opportunity to present at the Undergraduate Research Conference at Lone Star College C.R.A.T.E.R. To encourage further participation in this event, we opened the conference by sharing the amazing time that we had at TSGC and all the lessons learned from working to this project. Moreover, this semester we participated in a day in STEM in collaboration with the Harris County Public Library, where we share our experience in TSGC with young students by teaching them about the engineering process with hands-on activities where they got to go through the design process themselves. Lastly, we collaborated at the Science Olympiad to encourage young students to keep pursuing their dreams in STEM. The team had a fun time overseeing students as they created their own space-themed video games. Team C.R.A.T.E.R has put their heart into this project, resulting in a working prototype. But we're not done yet. Although the team had some delays in the manufacturing process caused by COVID-19, the team is in the process of building their prototype mostly of aluminum to get it tested at the Neutral Buoyancy Lab in September. Also, the team is working closely with the advisor to get a manuscript published about the ARM device.